Right, let's get into Chapter 8, Nonlinear Programming. So we have finally kind of exhausted the limits of the linear engine in Solver. And so there are just some problems, although we like the linear solver, and it is by far the most reliable. It's just not suitable for every type of model. So we're going to get into using the nonlinear engine in Solver and helping to make the kind of decisions that just can't be put into linear format. So, nonlinear programming. Solver uses the GRG engine for the optimization of nonlinear models. Okay? Now, GRG engine can be used to solve linear optimization models. And in fact, some of you, and I've done it too, have left Solver on GRG when we've solved linear programs. But as some of you have experienced, it doesn't always give you the same optimum as the linear solver. Okay, that's because the linear solver is guaranteed to find the global optimum, but the nonlinear engine is not. So the GRG engine is most appropriate for smooth functions. All right, so no gaps or kinks, although it will attempt to solve any problem that you give it. It just doesn't always do it very well. So these are examples of non-smooth functions. We've got a gap and we've got a kink. Okay. Now, as I say, the nonlinear engine will attempt to solve these problems, and they might do it might do okay. But typically, it is for smooth functions where if you graphed it out, it would not have gaps or kinks. So let's talk about one variable models. Okay, the nonlinear solver uses what's known as the steepest ascent method, assuming that we're looking for a maximum. So, for example, starting from any point on the graph, the procedure identifies the direction that rises the fastest and moves in that direction. And it keeps going until the function no longer increases. Now, but take a look at the function here. Okay, we have what are called local optimums. And so point B and point F are local optimums. In other words, if you started at point A and the solver moved toward point B, when it got to point B, it would stop. Okay. And it would return whatever value was at point B. Now the problem is this is only a local optimum. It is not the global optimum. The global optimum is obviously point D. Okay, and so this is one of the limitations of the nonlinear solver is that it will find a local optimum, but it is not guaranteed to find the global optimum because it doesn't know. You know, when it's moving up that line towards B and it gets to B and it starts to head back down, it doesn't know that the function will ever come back up. Okay, and so you end up with an optimum that is less than ideal. Okay, so let's compare the linear and the nonlinear solver. The linear solver will always find the global optimum if it exists. It will always find the same solution regardless of what values are placed in the decision cells before you run solver. And it is also suitable for linear models with integer constraints. All right. The nonlinear solver will always find a local optimum if it finds a feasible solution at all, but not necessarily the global. And it will function differently depending upon how you initialize the cells. Okay, so if the cells are all blank, it may find one type of solution. If you put 10 in all the decision cells, for example, it might find a different solution. And it is not suitable for models with integer constraints. Okay, so let's take a look at Crowley Foods. All right, so we have an inventory item that has a demand of 5,000 cartons per year. The cost is $35 for every order that we place. The unit cost is $30 a carton. The carrying cost or holding cost of inventory is 10% per unit per year. So in this case, it will be $3. Our objective is to minimize our inventory cost, which is the ordering cost plus the carrying cost. So the decision variable for this model will be the order quantity. All right. So the number of orders will be our demand, which is 5,000, divided by the quantity. All right. Our fixed cost, which is $35 an order, will be 35 times the number of orders. Okay. The average inventory level, we're just going to say it's X over 2. All right. And this is something that you would get from your inventory manager, your warehouse manager. So our carrying cost is going to be 10% times 30 times the average inventory level, which turns out to be 1.5 times X. So follow the algebra through. All right, go back over it if you need to. So our function, f of X, is 175,000 divided by X plus 1.5X. All right. And so you ought to be able to see from looking at this that this is not a linear model. Okay. So this is what the spreadsheet model looks like. Okay. And so again, this has been graphed out. This is not linear. All right. And so the order quantity is that 100 is just an arbitrary value. Okay, it is not our optimum. Okay, but as you can see, what we've done is placed a bunch of different values in the lot size and tracked the objective. Okay, and so you can see that the optimal quantity will be between 300 and 350. Okay, if we're trying to minimize cost. All right, and on the left-hand side, you can see the objectives. There are the calculations that lead to the objective. Okay, and as I said, it was between 300 and 350. It turns out to be 342. Okay. Now, the solver engine here reports that it has converged to the current solution. All right. Now, what that means is it's not absolutely confident that it has found the best solution. It's just that it's been trying for a while and has not noticed a lot of improvement. Okay. And so it stops. Actually, if you run solver again, it will often give you a different message. So we run solver again, and as I said, it says solver finds a solution or found a solution. It says all constraints and optimality conditions are satisfied. All right, and this will often happen. You'll have to run solver a second time to get the found a solution message, and it will very often be the same objective, the same results as the previous slide. And in this case, it is. Now, local or a global optimum, okay? Some things that we can do, all right? We can do a sensitivity analysis and plot the results to identify if there are multiple optima, okay? And that's basically what we did in the previous slide. We ran, we used Excel's data table, all right? And if you don't know what the data table is, pause this and take a little time and look it up. Okay, it's how you do regular sensitivity analysis within Excel. All right, and so if you see humps, then you'll know that there may be multiple local optima. We can run solver from different starting points to see if the results change. As I said, if we initialize the cells with different values, solver will often come up with a different solution. Sometimes there just isn't a good way to tell for sure. So let's look at a price discount for Crowley Foods. Purchase price was a constant in the last example, so we could ignore it. All right, but in this example, we're going to put a quantity discount on price. So anything less than 100, it costs $30. From 101 to 500, it costs $29.50, and from 501 or above, it costs $29.40. Okay, so this is going to result in a very different graph. So take a look here. All right, we have added in our thresholds for quantity discounts. And what we've done, if you look down here at the bottom, we've used an if statement. Okay, now this is something that is kind of new. You probably are familiar with if statements in Excel, but up till this point we couldn't really use them because if statements don't work with the linear solver. Okay, so basically the if statement is saying if the quantity is within a certain range, it's one price. If not, it's a second price or the third price. Okay. Now notice also that the graph has some pretty obvious kinks in it. All right. Now, and so this is not actually the best example of the use of the nonlinear solver because we've got these big kinks. But in our case, this is the best way to demonstrate local versus global optima. Okay. So for example, right here, we can see that there is a downward facing hump here. Okay, so if we started here and we worked our way down, we'd get to here and we would say, oh, we've reached an optima because then it would start to head back up. But if we start here and head down this way, this obviously is the global optimum because we're trying to minimize costs. Okay, and so this is the difference on how we initialize the cells, and I'll show you that a little more clearly in the next slide. So if the initial x value is less than 215, then our final value is 500. If it's between 216 and 499, we get 342. Then if we go above 500 but less than 2304, it's back up to 500. After 2305, it's 342, and so on. So the initial value in the decision cells matters with the nonlinear solver. And as you can see, you get very different optimums depending upon how you initialize it. So it does not hurt to either graph it out or to run multiple starting points to see whether you've got a local or a global optimum. Okay, so one way to aid in doing this is through the multi-start option. Okay, Solver's GRG engine has, that's the nonlinear engine, has a multi-start option that randomly starts Solver from different starting points. Okay, and you can actually, I don't want to get into population size or random seed right now, but this can be helpful. Okay, in actual real life examples that I've done, or textbook examples actually, it hasn't helped a lot. But if you have a big model and it's very, very nonlinear, then the multi-star option might help. So two variable models, okay? This is known as curve fitting, all right? And what we want to do is find a smooth function that fits the observed data points, okay? And some of you guys have probably done this when doing some statistical analysis or regression, things like that, all right? We have this data. It lays itself out in a certain pattern. What we try to do is find a function that best fits the observed data points because that allows us to predict future data points. So let's take a look at Fitzpatrick Fuel. They are seeking a model to estimate fuel demand based on outside temperature. Okay, and so for the first attempt, we're going to try a linear function. Y equals a plus bx. All right, and so let's move on. So the spreadsheet model, okay, we've laid it out here, the data from the previous slide. All right, the days, the gas consumption, and the predicted values, okay, and then the difference between the predicted values and the actual values, okay? So we let solver choose the A parameter and the B parameter, and the way that we assess the fit of the model is through the use of the sum of squares, okay? And again, if you are familiar with statistics at all, you know that this is a very common method of assessing the quality of a model. So basically, it is the sum of the squared differences. We square them, at least in part, to get an absolute value so that we're not dealing with positives and negatives. There are some other reasons as well, but this is a very common thing. So what we want to do is we find the parameters for A and B that minimize the squared error, basically. Okay, and so on the right hand side, you can see in the chart that blue is the actual data points and red is the predicted data points based on y equals a plus bx. Okay, and x is the degree days. Okay, and so it cuts a line pretty well through there. Okay, and we have a sum of squares of 3053. Now we can use what's known as a power model, y equals ax to the b. All right, and so we again let solver choose the values for a and b. Again, we are trying to minimize the sum of squares, and you can see that this model, the power model, is actually a little bit better. Okay, graphically speaking, it's hard to tell the difference, but the sum of squares is definitely lower. So this turns out to be a little bit better model. So let's take a look at the location problem. All right, we've done location problems in the linear solver. Okay, what this usually assumes is that we have a significant information about the potential locations, such as fixed costs, transportation costs, and so on. But using the nonlinear solver, we can actually look at this problem in a bare bones way, or a very basic or preliminary way, such as the raw distance between sites. And you've done something like this actually way back in chapter 1. So Merrill wants to locate a new warehouse to service 10 retail sites. The objective is to minimize the sum of the distances between the chosen site and the retailers. This is exactly like the homework you did in chapter 1. So the spreadsheet model is here, and again, you've done this. We want to find the location of x and y that minimizes the total distance, and we use the Pythagorean theorem to find the distances. Notice also that we're not so picky about the layout of the model using the nonlinear solver. Okay, I still want the spreadsheet models to be clear. I still want them to be able for people to understand them. Okay, but sometimes they can be laid out in a pattern that is different than when we use the linear engine. Okay, so the process of using constraints is the same with nonlinear models as the same with linear models, but the expectations are a little bit different. So for example, if we say that A is greater than or equal to, X is greater than or equal to A, and X is greater than or equal to, let me start that again. X is greater than or equal to A. X is less than or equal to B, and the objective is to minimize X. With linear programs, there's always going to be a binding constraint, all right, because it's a line. If it's going to go down, it always goes down. So if we don't put a halt to it, it'll keep going forever. But with nonlinear models, there isn't always a binding constraint. Okay, so just take a look at it here. As you can see with the linear model, X could continue to simply go down without with the linear model. X has to be located between A and B. Okay, those are the constraints. One of them will be binding. All right, but with the right-hand model, the nonlinear model, X is going to be somewhere around S. All right, and so there's not going to be a binding constraint. So let's take a look at the Nell's Furniture Company. The sofa, the demand curve for the sofas is 220 minus 4.4x. For tables, it's 180 minus 0.2x. Price is the volume. I'm sorry, P is the price, X is the volume. The variable costs are $60 a sofa and $45 a table. We have two constraints, 800 hours of assembly and 500 hours of inspection. Sofa requires 2 and 2, tables require 3 and 1, and the objective is to maximize profit. Okay? So, here's our spreadsheet model. Okay? Our decision variables are how much of each type of furniture to make. Okay? We have our price, we have our cost, we have our profit. All right? And we have our constraints. And so, as you can see, assembly ends up being a binding constraint. In this case, inspection is not. This is so. Other than the fact that the calculation is a nonlinear function, this looks just like what we've done with linear models. So the sensitivity report, if we want to do a sensitivity analysis, it's a little bit different for nonlinear programs. Okay, in the variable cells, we have a parameter called the reduced gradient, and so this will be 0 if the variable does not lie at a boundary. Okay, and for constraints, the what we used to call the shadow price is now called the Lagrange multiplier. And notice that there is no range, no allowable increase or decrease, because if you change the constant, okay, if you change the value of the constraint, then the shadow price will change. Okay, so there is no range. So let's take a look at portfolio optimization. Okay, a stock portfolio are typically evaluated by two measures: risk and return. The amount of variability in the performance of the stock is the risk, and the percentage of growth in the value of the stock is the return. Okay, so here we have 5 stocks. We have an average return, okay, and the standard deviation, which is a measure of the variability. Okay, so our objective is to assign proportions of our total investment to each stock of those 5 stocks to either maximize return or minimize risk. All right. And so we want to, in this particular example, we're going to minimize our risk subject to a lower bound on the return of 1.5%. So we want to minimize our risk, all right? But we can't minimize it forever or else we'll never get any return. So we put a lower boundary on the return, all right? The return is the sum of the proportions multiplied by the average return, and the risk is the sum of the squared proportion multiplied by the covariance between the returns of each pair of stocks. Okay, there are Excel functions for all of these things, so don't let the risk calculations scare you as if you're going to need to remember what risk is. Okay, this just happens to be how it is calculated in this instant, and so we're going to work with it. So here we have the spreadsheet model. On the right-hand side is the data. We have 24 months of data. We have the 5 investments and their returns for each of those months. Okay. On the left-hand side, we can extract some data. The average return is simply the mean. The standard deviation, there's an Excel function for standard deviation. And covariance is the measure of how two variables change together. Okay, and so these are the covariance, and there is a covar function in Excel. Okay, so these are how the different pairs of variances will vary together. Okay, our decisions are our proportions. So what proportion of our total investment, and we don't really even have to put a dollar value on our total investment. They just have to add up to 100%. Okay, so the decision variables are our proportions. Now we have various calculations here for risk at the bottom, and I mentioned what the calculation for risk was on the previous one of the previous slides. So, and we have essentially two potential objectives, either risk or return. Okay, so we can minimize risk, and in this case, we minimize risk and subject to a minimal a return that can go no lower than 1.5%. And of course, when you are minimizing risk, it's your return is most likely going to be at the constraint boundary. Okay. Likewise, we could also do this by maximizing return subject to a certain maximum risk. Okay, so we have something that we call the efficient frontier. Okay, and that is if we minimize risk while we vary the return floor. Okay, we get a set of data points. We can graph them, and this is the efficient frontier. This is basically the area that gives us the risk that we want for certain minimum returns. Okay, and we can also do it the other way. We can maximize our return while varying the risk ceiling. Okay, why do this? Because a lot of decision makers like to see things graphically. Okay, and so we graph them out. Okay, and so this is fairly standard in portfolio management. Efficient frontiers. Okay, let's talk about linearization. Because the linear solver is the preferred method of solving models, it's preferred because it finds the global optimum. So we prefer to use it when possible to the nonlinear engine. Okay, so sometimes it's possible to reformulate a nonlinear model into a linear alternative. So let's linearize the maximum. Excel's maximum function is not compatible with the linear engine. Okay, we could use the nonlinear engine, but we can never be sure if we have found the global optimum. Okay, so what we can do is introduce a new variable y that represents the max. Okay, so follow along here. Let's take a look at Armstrong Advertising. Armstrong has a number of projects, and they have 4 departments that are capable of handling them. To distribute the work, the objective is to maximize to minimize the maximum number of days that any one department devotes to projects. So we have 8 projects and the number of days that each project will take. So we need to divvy these up amongst 4 departments, such that we want to minimize the maximum number of days that any one department devotes to the projects. So here is the spreadsheet model for the nonlinear solution. It's actually pretty straightforward. We have our departments, decision variables is essentially which department gets which projects. All right. And so the 4 departments and the 8 projects are laid out in matrix format, and The total time is simply a sum product of the row times the time, okay? So that each of the, so this, there's a 1 here, so it'll be 65 plus 10. Obviously, this turns out to be 75. And so the objective is just the max of these totals, okay? The problem is that this doesn't work with the linear engine because the max function, a lot of the cool Excel functions don't work with the linear solver, okay? So here's the linear solution. It's a little bit different, laid out very similar, okay? But our objective is also a decision variable, all right? So that's a little bit new. We've never done that before. The objective is also constrained to be less than any of the, I'm sorry, the objective is constrained to be greater than any of the totals, okay? So J7 to J10, all right, is less than this value, okay? So it's a way of pulling off a max function without using the max function, all right? And so that is that's pretty handy. And of course, we are minimizing our objective. So because we do that, it will end up being exactly the same as the largest of these values. Okay, there's no point in having it be any higher than that. So here we have taken a nonlinear function, all right, and worked some magic on it so that it is now linear. And now we can use the nonlinear solver so that we can be sure of a global optimum, the absolute best optimum that we can have. So let's talk about another type of linearization, and that is linearizing the absolute value. Like max, the ABS value, our absolute value function, not compatible with the linear engine. All right, we can use the GRG engine with it, but we don't know if it's a global optimum. So what we do is we introduce two auxiliary variables, U and V. Okay, and so we're going to take a look at the example of Armstrong Advertising. Okay, they're still concerned that the workload between the departments is inequitable. They would like a solution that minimizes the sum of the differences in total project days between any pair of departments. Okay? So, here's the nonlinear solution. At the bottom, we've calculated all of the potential pairs and the delta, or the difference between them. Now, obviously, these are negative values. So what we do is we want to minimize the maximum of the absolute values. So we have to use the ABS function, all right? Not linear, okay? So we can't really do this and know for certain that we have a global optimum, okay? So this is what we do. We introduce two values, U and V, okay? And so we have, and the U and the V values become decision variables just like all of the rest, okay? And so we have our pairs, we have our delta be between the pairs, okay? And then we take the U value and the V value, and the delta is minus U plus V, okay? And what we have done is we've constrained the delta between U and V to be equal to 0, Okay, this is essentially a way. Work this through. Your head may be spinning at this. Okay, but essentially what we've done is we've found a way of finding the absolute value without using the ABS function. Okay, and so the sum of our differences now is 27. All right, and in fact we end up getting the same solution as as the previous problems, but we've done it in a different way, and we've done it in a way that guarantees that we have the best possible solution. Okay, in summary, the nonlinear engine is sometimes necessary, but it's not as reliable as the linear engine. There are some things that we can do to improve the confidence in finding the global optimum, such as doing a sensitivity analysis and graphing it, finding or starting with different initial variables, or using Solver's multi-star option. In some cases, there are methods, as we've just seen, for transforming a nonlinear model into a linear model so that the linear engine can be used. They can be a pain, all right, but it can be done. So, and finally, here is a summary of the different advantages or disadvantages of the linear solver versus the nonlinear solver. Okay, that's it for chapter 8, and we will catch you at the next chapter.